Now we're going to be going over robustness and probability analysis in RANSAC. So key concepts: proportion of inliers. So G represents the proportion of inliers in the dataset. Inliers are the data points that correctly fit the model. Inliers are data points that correctly fit the model, and outliers are those who do not. Number of pairs. So the number of point pairs needed to estimate the model. P. For homography, P is equal to 4 pairs are required. Homography is transformed between two views of the same scene. And probability of checking P inliers. So it's basically G to the power P. The probability that a randomly selected sample of P pairs will all be inliers. If G is equal to 0.5, it means half the points are inliers, so the fraction is half. And the probability of selecting 4 inliers at random would be G to the power 4, since P is equal to 4 for a homography. Right. Now, probability of not picking inliers after n iterations. After selecting n iterations, the probability that no valid inlier set was chosen is 1 minus G to the power P to the and the whole to the power P. So this is the correct formula. This is because each iteration independently selects a random sample, and the term 1 minus G to the power P gives the probability that the chosen sample is not all inliers. So this is after n iterations. So this is the formula. When you have an example calculation, you can go over that. I'll attach a link for that later in the description. So you can go. So explanation: inliers versus outliers. The core idea here is that while outliers may contaminate the data, inliers are consistent with the model. The algorithm's goal is to find a set of inliers, and the larger the proportion of inliers, the fewer iterations are needed to guarantee finding a good model. So this is a very important point. Algorithm's goal is to find a set of inliers, and larger the proportion of inliers, the fewer iterations are required to guarantee finding a good model. So more proportion of inliers is better for us. So impact of iterations: the probability calculations show the efficiency of RANSAC. For example, with 100 iterations and a 50% inlier rate, there's still a small chance that no valid inliers will be selected. With 1,000 iterations, the probability of failing to find a set of inliers is practically zero, showing that more iterations make RANSAC more robust in selecting valid models. Okay, so key takeaway: RANSAC's robustness increases with the number of iterations. However, if the proportion of inliers is too low, G is small, more iterations are required to achieve a good result. Conversely, a higher proportion of inliers makes the process more efficient. Robustness example. So this is basically the slide, you can go through it. Conclusions: this is a very important slide. So key concepts: effect of the number of parameters of the model, number of necessary pairs. So bad exponential. As the number of parameters P increases, the number of required pairs grows exponentially. For example, in the case of homography, which requires 8 parameters, more pairs will be needed, and this can increase the complexity and computation time of RANSAC. This means that more complex models require more data points to be sampled, making the algorithm computationally more expensive. Okay, so bad exponential. Effect of percentage of inliers G. So base of the exponential, the proportion of inliers G plays a critical role in the efficiency. As G increases, the probability of finding a valid model increases, which means fewer iterations are required. So basically as G increases, more inliers are required. As G increases, it means that there are more inliers. The probability of finding a valid model increases, which means fewer iterations are required. The percentage of inliers affects how quickly the RANSAC will converge. Higher G reduces the number of iterations required to reliably fit the model, making it efficient and making the RANSAC algorithm converge faster. Now, effect of the number of iterations n. Good exponential: the number of iterations is critical. The number of iterations grows exponentially based on the likelihood of correctly picking inliers related to G and P. However, more iterations lead to higher probability of finding a valid model, especially in presence of noise and outliers. If n is large enough, the algorithm becomes highly reliable, as shown in previous calculations, where n is equal to 1,000 leads to a near zero probability of failing to find a model. So now we go over to the recap. So basically, for fitting a model with low number of parameters P, homographies are used as an example, where P is equal to 8 parameters for the transformation matrix. It works efficiently when the number of model parameters is low, as fewer parameters mean fewer data points are needed to compute the model. Right. Now, RANSAC loop: select P random data points, choose a small subset of points enough to define a model. For homography, you need at least 4 point correspondences, but typically more are used. To fit model, use these points to compute a potential model or transformation matrix. For example, and count inliers. Identify the points in the dataset that fit well with the computed model, those that have a small error and fall within the threshold of the homography transformation. Fourthly, keep the model with the largest number of inliers. After several iterations, the model with the largest number of inliers is selected as the final goal.